So in this screencast, we're continuing our journey into addition reactions, and we're going to talk about halohydrin formation. I think that one of the more challenging things about this chapter is that everything kind of sounds the same. And so I want you to notice that a halohydrin, here's a way to differentiate it. We are adding a halogen here. It's X2, so it's either going to be Br2 or Cl2, but we also have water. So when you have both of these things, you form a halohydrin, which is a halogen attached to a carbon next to an alcohol functional group. When we look at this would be a specific example. For example, this is a chlorohydrin. Now, let's look at the mechanism of this, and it's going to react really similarly to the previous mechanism for halogenation that we just looked at. So we're going to start out with our friendly alkene here. And again, we're going to use a generic halogen. Okay, and same thing happens, right? It comes close to the nucleophile. We induce a dipole in this molecule, and these electrons come out and they attack that. Those electrons come down, they attack that carbon, and then those electrons go back on that halogen. Now, it's the exact same first step, and we form the same intermediate. So we get that bridged polonium ion again. All right, so there's our bridged polonium ion. And what happens here is that water comes in, and so instead of the halogen here, water is used as our solvent, and it's going to come in and it's going to attack. And when it attacks, it's going to open up the ring. Now, when it opens up that ring, right, we end up with this protonated alcohol. And so I don't know what I just did there, so let me get rid of that. Let's see, water is going to come back in here, and it's going to steal that proton, and those electrons are going to go right onto that oxygen, and now we have formed our halohydrin. I kind of got wild over there, but that still works out with those electrons. Just like that. Okay, so I want to point something out here, because maybe the burning question in your heart is, hey, we're still forming X minus in this reaction. Couldn't X minus come up and attack here like we saw in the halogenation instead of water? Well, yes, it's possible, but what's really going on here is this concentration is really small compared to water, which is going to be our solvent here. And so there's just so many more of these molecules that this is the predominant reaction we're going to see. So water there's acting as the nucleophile, not the halogen here. Now, other reagents can also be used to do this reaction. Another reagent that's often used, right, is N-bromosuccinimide, which is abbreviated as NBS. And you'll see it in reactions like this, generally in the solvent DMSO. And I just want to remind you, DMSO is got the structure that looks like this, right? To form, in water, to form this bromohydrin. What happens here is NBS, right, in water will decompose to give that Br2, which then goes on to form the bromohydrin using the exact same reaction mechanism. So this is the same reaction mechanism as previous slide. You just start with the Br2. Okay, so if you have MBS, that needs to give you a signal, hey, look, we're going to start that mechanism with Br2 right there. Okay, so don't let that throw you off. All right, let's talk about stereochemistry for a little bit. When we talk about this, stereochemistry, we're going to see some of the same things that we saw with the halogenation. So because we have a bridged polonium ion and it's opened with a backside attack of the H2O, right? You see an addition of the halogen here and the alcohol here. It occurs in an anti-fashion. Right? And so, sorry, in the OH, it occurs in an anti-fashion. And so what that means is you get both of those trans enantiomers. Now, notice this is a symmetric example. And so maybe the burning question in your heart is, what about an unsymmetric alkene? And I'm so glad you asked. If we look at an unsymmetric alkene where, and what I mean by that, because this still has symmetry, obviously, but what I mean by that is where the number of hydrogens here and here are different. So this, when we draw it out, and my suggestion honestly is to draw this out when you first get started so you can see the hydrogens so that you know where the addition's occurring. So with unsymmetric alkenes, the preferred product, which is here, has the electrophile, which is X plus, bonded to the less substituted carbon. Right? And if we think about Makovnikov's rule, right, where we were dealing with H plus, what we find here is if this were H plus, the hydrogen would come down here and join this carbon, right? Because it's the less substituted, or it has the one with the more hydrogens. X plus does the exact same thing because the mechanism is similar. So X plus is going to come down here and it's going to go to the carbon with the most hydrogens, right? And so we see that here. And then the nucleophile is going to add over here. Now let's look at this mechanism. When we look at this mechanism, we see the addition here with the bromine coming down to form the three-membered ring here. And what we find is there's a nucleophilic attack on the more substituted carbon. So the reason that occurs is because this carbon is better able to accommodate a partial positive charge in the transition state. And so that's why we end up with the halogen on the less substituted carbon because it opens this way. Now, let's look, I do love a good summary. Let's look at a summary. So here's the summary of halohydrin formation. The mechanism involves 3 steps. The rate determining step is the first one, and it forms a bridged polonium ion. No rearrangements can occur, which is always nice because we don't have a carbocation intermediate. The electrophile bonds to the less substituted carbon, and then anti-addition occurs. So really nice summary there. This is, halohydrin is, a reaction is used in synthesis. So I always love a good example. This is an example of a natural product. It's a female sex hormone called estrone. And when this is synthesized in the laboratory, one of the steps is the formation of a halohydrin, which you see right here. All right, this ends our screencast on halohydrins. As always, if you have any questions, please feel free to stop by my office.